All right, we're going to start here going through the energy test answer key. So we'll start with this first conceptual question here. So we have these three different boxes all going down ramps. As we can see, the ramps have slightly different pathways. And in both cases, for both parts of the question, we're really concerned about how fast the box is traveling at two different spots. So the first one is this halfway point. And if we think about that, really the key to this is gravitational potential energy. That's being converted to kinetic as they go down, and in all cases we have this energy transfer occurring. So what really matters, what really will affect the amount of kinetic energy, is how much gravitational potential energy we transfer. So the key to that is height. Okay, so if we look at these three situations at the halfway point, we see that box A drops from the top of the ramp down to that level part, a difference of h. Box B drops from the top of the ramp down to that level part, which is actually going to be greater than h. And box C drops from the top down, partway down, which will actually be less than h. So that's really the key for this one. B has the greatest change in height, and therefore that means B will be traveling the fastest at that point. When we move on, though, and consider the end of the ramp, what we end up seeing is they all start and end at the exact same height. And even though their pathways of getting there are very different, A gets there almost immediately, B actually drops down below and then comes back up, and C gradually goes down the entire time. What really matters is at the end, all of them drop a height of h, and that means that they'll all be traveling at the same speed. This next problem here, we want to find the work done compressing a spring. And so we have two options for work. We can either do F delta x cosine theta, or we can find the change in energy. Here we're just going to find the change in energy. And the energy that's changing specifically is going to be our spring potential energy, US. So what I'm going to do is I'm going to take my final spring potential energy minus my initial, and that's going to get me my work done. So it's going to be 1/2 K x final squared minus 1/2 k x initial squared, because we're compressing it from a length of 0.9 meters to 1.3 meters. So because it's already compressed and we're just compressing it further, we need to just find that change in potential energy. So going ahead and plugging in what I know, my spring constant K is 900. That final compression distance is 1.3 squared. And then my initial compression distance is 0.9 squared. And so I end up getting that my work is 422.5. That's my final spring potential energy, minus 202.5, which is my initial. So the work done is just 220 joules. For this next problem, we have another situation where we're trying to find the work done, but here we're given a force and a displacement, so we're actually going to use our F delta x cosine of theta definition here. And so what we're thinking about is a box that's sliding across a level floor. So we'll say it's sliding to the right. That's important because that's going to be the direction of our displacement. And then we have some forces acting on it. The two we really care about are the force of friction, which is going to be going to the left, and it has a value of 6 newtons, and the force of gravity, which is going down, and it has a value of 19.6. It would have a normal force as well, and possibly something else, but we don't really care about those in this situation. So for the work done by the force of friction, we're going to say it's going to be 6, which is our force of friction, times 4.5, which is our displacement, and then our angle is going to be 180 degrees, and that's because the angle between that force and that displacement is just 180 degrees here. So we end up finding that our work done is going to be negative 27 joules. Okay, it is important that we have that negative. That indicates that that force of friction is causing the object to lose energy. We can do the same thing for the force of gravity. Okay, but obviously we're going to use the force of gravity, which is 19.6. Displacement is still 4.5, but the angle is going to be 90 degrees now. And we see that looking here, there's our 90-degree angle. And that makes sense because as it goes across the floor, Gravity is not going to add or take away from its energy, and that's really what work is, the change in energy from that force. So it makes sense that there's no work being done by the force of gravity here. All right, for this next problem, we have this block being pushed up against a spring here, being launched along the ground and then eventually up a ramp. And we first want to think about the energy bar chart for that motion. And so what we're going to think about is what energy do we have at point A, point B, point C. So at point A, when it's being compressed up against the spring, we obviously have spring potential energy here. It's not moving, it doesn't have a height, so that's it. As we go from A to B, we're told that the surface is frictionless the whole time, so there's no work being done here by a non-conservative force like friction. So all of that spring potential energy is going to become kinetic energy here at B. It still doesn't have a height. There's no longer a spring being stretched or compressed here, so it's all spring potential energy. And then as it slides all the way up to the top, it comes to rest, we're told, so there's no more kinetic, but we do have a height now, so all of that energy is gravitational potential. So your bar chart should be all spring potential, all kinetic, and then all gravitational potential, and the same amount at each point in time, because it's just being transferred from one form to the next. In terms of the math part here, we want to first find the speed of the block at point B. So we're going to start, of course, with our big equation here, E initial plus work equals E final, and we're thinking about that transfer from A to B. So we're starting with spring potential energy. There is no work done here, and we end with kinetic. So what we end up getting is 1/2 kx squared equals 1/2 mv squared. And so we plug in what we know. Our spring constant is 900. We know it's compressed a distance of 0.8 meters, so that's our x value. And that equals 1/2 times our mass of 25 times v squared. So we end up getting 288 equals 12.5 v squared. So 23.04 is v squared, which means v, just taking the square root of both sides, is going to be 4.8 meters per second. So that's for part A, or for part B, I mean, the velocity at that point. And then we move on to part C of this problem, and what we want to find here is the value of this height that we reach. So we're going to set up our energy once again, E initial plus work equals E final. Now you do actually have a choice here. You can either think about the object going from A all the way to C, all right, so going from all spring to all gravitational, or now that we know the velocity at B, we could just go from B to C and just do the kinetic at B becomes the gravitational potential at C. It really doesn't matter. I'm going to go back to the beginning and say US once again, so I'm going to be going from A all the way to C. No work done still in this one because we still don't have a non-conservative force doing work. But now we're going to end with gravitational potential energy. So it's going to be 1/2 kx squared equals mgh. Same values that I had in part B, so I actually could take a shortcut and just say that that energy is still 288. But I'll write it out here anyway. But now we're going to gravitational potential energy. So mgh, so we get 288 equals 245 h. So my height here is going to be 1.18 meters. All right, moving on to this next one. Now we have a person who's moving at a speed of 6 meters per second at the top of a 5-meter tall hill here, and they go frictionlessly down to the bottom of the hill, and we want to know the speed at the bottom. But we're first going to think about our energy bar chart. So when we're up here at the top of the hill, we have a height and we have a speed, so that means we're going to have kinetic energy and gravitational potential. It's tough to say exactly which one's bigger. We could figure it out, but really we're more concerned about the type of energy. So we should have some number of kinetic, some number of gravitational potential, but it doesn't actually matter how much of each. And then when we get to the bottom, all of that energy is going to be just converted to kinetic because we no longer have a height. So that's what your energy bar chart should look like. Again, as long as the kinetic and gravitational potential you start with add up to the kinetic you end with. It doesn't matter exactly how many blocks you have. This is just an example. Math-wise, what we're looking at is, again, we're going to start with E initial plus work equals E final. So we have UG plus K to start. No work is done here, once again, because there's no friction. And we end with kinetic. What I sometimes do is I'll say K initial and K final, just to indicate that even though we have kinetic at both places, we know it's not the same amount because the velocities are going to be different. So we can then say mgh plus 1/2 mv squared equals 1/2 mv squared. And once again, I'll say v final and v initial just to distinguish between the two. So we get m times 9.8 times 5 plus 1/2 m times 6 squared equals 1/2 mvf squared. Notice I'm not filling the masses because I don't actually know them, but once I get to this step, I see that I have mass in every single term, so that actually all will divide out, and what I'm left with is 49 plus 18 is going to be equal to 1/2 vf squared. And so I end up getting that 67 equals 1/2 vf squared, which means vf squared is 134, multiplying by 2 there. Then I take the square root and I find that my final velocity here is going to be 11.6 meters per second. All right, moving on to this next one. We don't have an energy bar chart to do for this one, but we are going to start with our E initial plus work equals E final equation once again. And so what I'm thinking about is we have this ball initially at some height here. We're told it's 2.7 meters above the ground, and we're going to exert a force on it, causing it to move to the right. So that right there, that 70 Newton force, is clearly going to indicate that work is being done. There is one key part here, and that's this piece in italics that we're assuming that after the ball is hit, it's still at a height of 2.7 meters. So what that means is, and there's a few ways you can handle this, we definitely start with UG, and then there's some work being done. And we're going to end with kinetic because it's moving, but we're also going to end with UG. And what's going to happen is the initial height, when it's before it's hit, is 2.7 meters, and the height after it's hit is still 2.7 meters. So what we can do, given that those two UGs are the same, since it's the same height, we can actually just get rid of them. And so really all we care about for this particular part is the work becoming kinetic energy. Even though we have gravitational potential energy, there's no change in that gravitational potential energy. It's the same on both sides, so we can ignore it for this part of the problem at least. So we're going to find our work done using f delta x cosine theta, and that work that we do on the ball is going to become the kinetic energy of the ball. So our force is 70, we're hitting it over a period of 0.82 meters, and our angle here is going to be 0 because whatever direction we hit it, that's the direction it's going to move. And so that's going to be equal to 1/2 times our mass, 0.05, times v squared. And so we end up getting 57.4 equals 0.025 v squared. So when we divide by 0.025, we get 2,296 is v squared, so our velocity ends up being 47.9 meters per second. For the second part here, we're now considering the ball when it hits the ground. Okay, so we're thinking about this ball that's already moving here at a speed of 47.9 meters per second at a height of 2.7 meters, and it's going to fall down to the ground, and we know when it hits the ground, it's traveling at a speed of 28 meters per second. And so we want to figure out how much work is done by air resistance as it flies through the air. So we're going to use our same equation here, but our setup's going to look a little bit different. And there are a few ways of doing it, but I'm going to consider basically this period of time shown in the picture. So my initial is going to be after it's hit, when it's moving at that speed of 47.9 meters per second, and my final is going to be when it hits the ground. So I'm starting with kinetic because we're moving. I'm also starting with gravitational potential, and now I do care about it because I am changing heights, so it does matter that we start with that gravitational potential. We have some work done here by air resistance, and we're ending with all kinetic energy. So once again, I'll call it initial and final. So we have 1/2 mv initial squared plus mgh, plus that work being done that I'm just going to leave as a w there because that's what we're ultimately solving for, the work done by the air resistance. And that's going to be equal to 1/2 m times v final squared. So we sub in our mass here and our velocity that we just got from part B. We have our height is that 2.7 meters above the ground, plus our work done by air resistance, and that's going to be equal to our final kinetic energy when we're traveling at a speed of 28 meters per second. We go ahead and do our math there, and I'll write out what each individual one is, just in case you want to check that. And so that's going to be equal to 19.6. So we end up getting that our work done here is negative 39.1 joules. Makes sense that it's negative because air resistance is going to cause it to lose energy. And so that's what we have for that one. All right, moving on to our final problem here. We have a softball player hits a ball with an initial velocity of 38 meters per second. It lands in the stands of bleachers at a height of 10 meters above the point where it was hit. And as it flies through the air, it loses 15 joules of energy due to heat from air resistance. So we're starting with kinetic energy because initially we're moving. When we get to the end, we're going to have kinetic still because we're still moving, and gravitational potential because of this height piece. But in between, we're going to have some work being done, and that work is actually going to be negative here because we're losing energy. All right, so that's what our bar chart would look like. We should start with all kinetic. Some of that is going to be lost, so that our total value should decrease going from A to B, and then we're going to end with some kinetic and some gravitational potential. And obviously that should all add up there. So how fast is it moving when it lands in the stands? We're going to once again set up E initial plus work equals E final. So we start with our initial kinetic energy, plus that work done by friction, which is this 15 joules. And that's going to equal our final kinetic, because we're still moving then, plus our gravitational potential, because we have a height, since we're starting on the ground and landing at some height, 10 meters above that final point. And so we can sub in our equations here. I'm going to leave this as WF because we're going to just put in this 15 joules. That is the work being done. All right. And then our gravitational potential. And so we once again sub in the things that we know. Our mass is this 0.145. Our velocity, the initial velocity at least, is 38. Minus those 15 joules, that's the work being done, and that's going to equal 1/2 0.145 v final squared, which is what we're solving for, plus the final gravitational potential energy that this object has. And so we end up with 104.7 minus 15. It's going to be equal to 0.0725 v squared plus 14.21. All right. We do a little bit of math here and get this number by itself, and it ends up being 75.5 is going to be equal to that kinetic energy term, which means that v squared equals 1041. So v is just 32.3 meters per second when we take that square root. All right, for the final part, we want to find the average force exerted on the ball due to air resistance. So we know the amount of work done by that force is negative 15 joules. We also know that our distance is 160. And if we think about the ball flying through the air, as it's moving to the right, that force of air resistance is going to be going to the left, that of course is an angle of 180 degrees. And so we can say cosine of 180, and that actually works out well because this negative and that negative will divide out. And so what we really get is negative 15 equals f times negative 160, because that cosine of 180 is just negative 1. So we find that our force here is 0.094 newtons.